Hi everyone. In this lecture 24, after briefly commenting on long chain branching, I will focus on describing to you the construction of the tube model. And then I will follow this by indicating the need to consider some new ideas and therefore start to introduce our own picture. So we are at the end of chapter 15 and we made a summary. And I think I just have one more thing to say regarding chain architecture so that so that everything will be clear. So you know, as soon as we move into chapter 16, we will start by reviewing what a tube model does. We will focus mostly our discussion on linear chains. There is a separate extension of the tube model to deal with long chain branching, for example. And that's just not something I'm going to cover. So I may just indicate here our framework that is discussing chapter 16 is also not going to deal much with architectural issues. So we'll only be dealing with linear chains, linear untangled melts. But as you know, in the book, there are a number of places where long chain branching. So I just want to indicate this issue once for all, and most of the time we will not talk about the long chain branching. So the first place we had long chain branching discussed, you know, you can go to the index. There's long chain branching many times. But in chapter 8, page 186, that's where I indicated that long chain branching allows the system to resist yielding so that you can have, for example, LDPE. So that you can have drawing for a large amount of stretching ratio without failure. And that's the role of long chain branching, first discussed there. And we also had some other architecture that's mentioned in that chapter. And then the place where long chain branching is also mentioned is page here. One question is about whether long chain branching could suppress shear banding or not. So that's not something we have done, but it's something in our mind, and it's further indicated on page 128 when we talk about vorticities, vortex formation at the die-entry. There is a suggestion that LDPE give you vortex formation because it suppressed shear strand localization that would occur in linear chains. So these are the few places where, one more last place I should mention about long chain branching is, of course, the place where I last time already mentioned on page 307, the long chain branching can fight against elastic yielding. Basically delays it, against localized elastic yielding during, or rather after, step extension. So these are the few places where the effect of long chain branching stands out. It's very dramatic. And we know roughly, if you understand the theory for linear chains, you get some appreciation why long chain branching could do this. So in fact, it was because of that. We had some understanding of what the theory for linear chain is, and that was the reason why we probed long chain branching effect in these few cases. Okay, so that's really just for completeness, because I'm not going to address architecture very much from this point onward. Okay. So with that, let's formally start chapter 16. Of course, it's a essential chapter talking about, it's basically theoretical discussions. If I were just casual about what we're talking about here. So we're going to discuss how to understand the phenomenology that we covered in chapter from 6 to 15, the phenomenology. So I will begin, as we should, by a slightly more quantitative and careful discussion about the tube model, so that we can see how it's built and whether it is inherently able to describe what we observed. Okay. So a lot is said in words, so you may find it helpful to even read some of these writings in chapter 16. So, but I will begin with 6, which is really a summary of what tube model does, what tube model is, and it does. You all know, or I would even indicate for you that the tube model is extremely successful if you confine yourself to the problem of linear response. Okay, linear response. Keep in mind, linear response. By now, I must have repeated more than 10 times. Linear response, as you know, means leaving the structure intact. What structure? Of course, entanglement. And how we are describing entanglement according to tube model? Well, tube confinement, right? And this tube constraint means such a tube exists for every chain in your system. In the linear response region, you don't need to bother about when do you lose such a constraint, because such a constraint will always be there, because that's the definition of linear response. Or at least that's the definition of very little deformation, so that you don't speak about disentanglement. Okay? So this disentanglement, as far as I learned tube model to begin with, it is not a familiar concept within the tube model to speak about disentanglement, to speak about the disappearance of the tube. Because in absence of the tube, there's nothing to be discussed in terms of what are the results of the tube model. So I want to mention that right away, and it will come back again and again, that the tube model might be very successful in the linear response region. The tube is simply impossible to disappear, because it's made of all the surrounding chains, and they cannot just disappear all of a sudden in a coherent way. That's why you always have tube constraint, and this enables you to speak about reptation, for example, all the chain dynamics and diffusion issues, in absence of large deformation. So there, of course, there's no disentanglement to speak about. But of course, meaning it turns out this is all addressed in the first 3 papers published in 78. And of course, we didn't stop there. The 4th paper, published a year later, it does talk about all aspects of non-linear response. To speak about it is to first talk about the, if you like, the premise of the tube model. So you can, of course, let me just more or less trying to be consistent with the book. A tube-like constraint exists. If that could be your first, the tube, oh Lord, the tube deforms finely. So this takes care of the possibility that you have large deformations, basically. And then, thirdly, which is a very crucial one, extremely crucial one, that it, if it's a rheological theory, it must know how to calculate stress. This is all where everything gets started. When you build a rheological theory, it actually starts from the common practice that we know the strength field is prescribed. Okay, it's already predetermined, the strength field, such as shear field. So you say everywhere has simple shear with a single shear rate. And then under that condition, you try to compute for how this chain behaves in terms of resisting or responding to the shear field in terms of giving rise to macroscopic stress. Stress is all intra-chain in origin. So this is actually a pretty big deal. And it's not all wrong, if I'm asked today. Although a great deal of confusion remains in the literature about, especially coming from molecular dynamic simulations, that seems to indicate the stress has interchain contributions as well. Whereas here, this idea really comes from the success of classical rubber elasticity theory. There we learned we can ignore any interchain interactions and just worry about the retractive force from deformation of the chains. And to complete the story, and a particularly important one, which we already mentioned previously with regard to how to think about large deformation. This last one is most elusive, meaning when I say elusive, it is the one that produces many of the features that appear to be in agreement with the experiment. That is the Rouse dynamics are assumed to take place in the tube. In particular, there is a Ross chain retraction after a fine deformation of any amount at tau r. So these are the building blocks, not building block, the ingredients that allows you to propose a very well-developed analytical theory for nonlinear polymer rheology. The effort is heroic because it's a very hard problem. And the approach is familiar in the sense it's a mean field. It's a mean field in the sense everything, all the other chains is being accounted for by acknowledging there is a tube and just concentrating on one test chain. And all the quantities can be calculated from the behavior of just this one test chain. So that's the tube model. We of course have to look at this how it's being constructed in order to see or to compare this with any other type of theory, and certainly to see whether this theory is able to handle the phenomenology we went through. As I indicated once more, should I indicate once more, that even under condition of nonlinear response, which typically means large deformation, and if you are careful, you know it will be complete by saying large, fast deformation. And by fast, of course, we mean Wi, much larger than 1, for example. That even under this large deformation, nonlinear response case, it is not clear we speak about disentanglement. Because how? Well, today, in response to so much experimental observations, to the narrative that we keep saying there is disentanglement, people start to say, oh, I don't think I'm putting my words in people's mouths, but people will start to say, hey, I do have a mechanism for disentanglement. That's this. But this has certain mechanical or rheological consequence, as I tried to indicate when I reviewed some of the tube model features. But itself does not give us a sense how the structure truly fall apart, because the structure falling apart is a many-body question. Because your system is a many-body system. Your system is, one chain, another yet, and they fill in the space. It's a many-body problem. Since we speak about disentanglement and speak about a Ross chain retraction, if you really wish to say that this is disentanglement, then there is one question here. The question is, there's one feature of the tube model, is that this disentanglement will occur with no barrier. It will occur on Ross time without sweat. It will simply would occur. And I probably will be more careful talking about this when we say further about the finite cohesion issue. This Ross retraction will occur It meets no barrier. And there's a question of whether that's consistent with observations. Okay. Yeah. Yeah. So the question was, what do we mean by barriers? It's almost like I cannot speak about that until two things. One is from our observations. Okay? We know, for example, in the simplest case, you have entangled melt, you make a filament, you draw it, let's say double the length. That turns out to be about enough. And hold it, it will break up. But if I don't go double or triple my length, if I only go 50% of my length, it doesn't break apart. So there is a barrier. Or if you like to see that failure is disentanglement, there's barrier against that disentanglement.
So in a scenario where you are considering this to be true, like Gaussian interaction is accounting for disentanglement. So even if I draw to 25%,
it will, whether your filament will fail or not is not clear, but it will. I wasn't planning to show you, but let me show you this again. It will produce deviation from linear response. So I know this is a figure for shear, but we have a separate figure identical in the case for extension. So this is all described in chapter 14 we just went through. That was the whole idea. No matter, so this is a gamma, but let's present same data. Lambda goes from 1. By the time, well, experimentally we observe, by the time of 1.6, you start to have deviation from linear response. But according to the two model, as you said, 20% of deformation. You'll find that 20% after Rouse time will retract. And that stretching contribution in other words, the amount of retraction, of course, depends on how much you stretched. Therefore, the observation, therefore, you never observe a feature of stress relaxation that is independent of how much you stretch. Because the more you stretch, the more of the retractive contribution of stress will retract, meaning the contribution due to stretching. So let me try to illustrate that. So you have a chain, you're stretching this much versus you're stretching this much. Let's say this is lambda equals 1, this is equals 10%, this is 20%. Okay? Because of the Rouse retraction, anytime after the Rouse retraction time, anytime longer than tau r, you will find that there is more stress loss here than here. Well, basically, you have a stress loss at 20%. That's a lot more than what you have at 10%. Okay? So, which means your stress relaxation is faster at 20% than at 10%. And so such a curve is exactly capturing that. So that you show that the stress relaxation is always lambda dependent. Because for this to go back to there, you lose more stress than from here to there. So in any event, this is, I think we'll come back to this point, okay? because I cannot, I will come back to it when we discuss our scenario for the theoretical picture of this. So let me just, again, just indicate what was discussed in the book. So there was so this is all some, let me just follow this point. Under the summary, there were many subsections. The first subsection is just about basically starting point of the tube model. And then I had a little separate section just to talk about Ross chain retraction. I'm not going to say further. You can go ahead and read that part. It has a lot to do with the issue of whether the deformation you have is fast or slow. And then I've focused on something that I already had the introduction for you, which is really the non-monotheisticity. I want to highlight that again. So under this title, there was additional breakdown of absence. This is just what we talked about, absence of linear response. Why it happens? It happens because of the chain, assume the chain loss retraction. The tube deforms finely. The more you stretch it, the more it deforms, and therefore the more chain retraction will occur. So that when you look at the stress relaxation, so this topic is all heavily discussed in chapter 14. So that if you look at your stress relaxation, you'll find your stress relaxation is always dependent on how much you have step strength. So I'm going to skip that because we talked a lot about that in chapter 14. And the second one is the next three topic is the three different types of non-monotheisticity that I have once before already indicated to you. But I will go into a little more detail perhaps. No. Monotonicity. We previously have discussed it. Let's do that more carefully one more time. I will do that by going to the next slide where I paste some of the diagram. Let's not look at the first one. Let's look at the second figure. This belongs to chapter 16. So what I was attempting to plot or to summarize is a case of first is a case of thinking about startup. So you either start up with constant shear rate, startup shear, or constant Hanke rate, startup extension, you will find, I'm trying to unify everything here for you. You will find that the shear stress will have a maximum. That's the Thiele model says so. Then if you do the parameter right, as we do with engineering stress, the Thiele model also have the feature of a maximum in the engineering stress. And that arises from the fact that if you look at the true stress, we call it Cauchy stress as function lambda, the Thiele model basically says it will soon reach steady state. Well, how soon? Sometime after. In fact, I should pause for a moment. Please allow me to pause for a moment. So, we talked about Thiele model here. We talked about the Thiele model as we know it. It turns out historically, the Thiele model was discussed in the following way. Mostly, the Thiele model was discussed in the limit where there's very little chain stretching. And of course, that is all fine except for the number 4. If there's very little chain stretching, there will be very little chain retraction. So let me try to slow down here to indicate that we will first concentrate on the conclusions of the Thiele model in this limit, where there's very little chain stretching. It turns out to stretch, this is something I'm not going to develop a theoretical argument for you because I think this remains the most elusive, if you like, or mysterious part of it. It turns out somehow your polymer chain in an untangled state lives on a clock, time clock of Ross time. If you, well, I say if this is true, right, it just means that your stretching is such that to make 100% deformation, this is what it is, right? Make 100% deformation will take a time longer than Ross time. Yeah, that's the limit. So basically, your chain is living on the clock of Ross time. If you are trying to deform me on time scales longer than Ross time, I will not be stretched. I will not be stretched. That's the same as saying this. So, which apparently our experiments seem to also indicate, but it's identified from the discussion of the Thiele model that in this limit there will be no chain stretching. So this is the terms that you probably only hear for the first time. So just be patient with me. We will hear a few more times. You'll start to get used to it. So I will discuss a lot of this first in the limit of very slow deformation. Slow in the sense of satisfying this. And although you can have your WI larger than 1. And we'll build the other parts in later. So in this diagram, I'm actually summarizing for you the result according to the Thiele model in that limit. Okay, so this is a summary of the tube model results in the limit of no chain stretching. Okay, so in that limit, then your extensional stress will reach maximum when one chain can no longer be further oriented in the stretching direction. So if this is the case, if you divide this by lambda, naturally there will be a peak. Okay, and that peak occurs at about 2 times of the repetition time. And keep in mind, this maximum is all reached at the time much larger than tau r, just by definition. So in any case, I'm trying to show you that just try to get this color correct. I'm trying to show you that that the tube model is capable of producing 2 maximums. One is in shear. I indicated before, we can do that one more time, that it turns out any additional, as you shear more, you basically, let's say your tau, what is it? So as you shear more, the stress cannot build up because your orientation start to it's all described in, so I don't think I need to go into any details. It's all described in Dwayne Edwards' book. So basically, you will reach a maximum because of chain over orientation, and the good news is the experiment also shows a overshoot. So it looks like it appears to show that the tube model can capture this overshoot characteristics without speaking about yielding. There's nothing about a structural failure in this whole picture or disentanglement. As I indicated, in extension, the maximum occurs because this stress drops because the load area start to decrease. Or rather, it always start to decrease. Rather, the sample becomes thinner and thinner. Okay? It becomes thinner faster than the force that can still still grow. So that, in fact, it no longer grows. That's the whole point. So this, okay, the stress can no longer grow because you already reach a steady state orientation. So you can no longer have your stress growing, meanwhile your area is shrinking. So of course your total force. Remember, engineering stress is about the total force. So of course your total force will start to drop. Okay, so this is of course this feature is discussed in paper 4, and it was combined with the considerate criteria to argue that that this could give you a necking. Okay? Because they also seem to be aware that the sample could become unstable. But this failure, considering necking, speaks nothing about structural failure. So it's very strange, as if it's a mathematical failure of some type. It's very, very strange. So you have to really go back to this original paper to appreciate what was going, how they are reporting this. In the very same paper, now you can look at your shear problem in steady state. If you calculate the steady state stress at different rates, I know I'm drawing just arbitrarily now. At the different rates, you will basically be able to read the steady state stress, shear stress, and you plot that as a function of shear rate, you also had a maximum. That was what I told you before. So we're already speaking about three maximums. In startup shear, there's a maximum. In startup extension, this is all extension here, right? So in startup shear, there is a maximum. In startup extension, there is a maximum. When you think about steady state shear stress as function of shear rate, there is a maximum. Because at higher shear rate, you can orient your chain more. But over-orientation doesn't give you more stress, actually give you less shear stress. Because the chains become more aligned to the shearing direction. And this, of course, this versus that is a crisis because you cannot have stress going down as you shear faster. Okay? So this is what we reviewed in chapter 15, that constitutive non-monotheisticity, shear banding. So in the fourth paper, it's an absolutely amazing paper. They suggest there's shear banding because the thing goes down as function shear rate. And they also suggest there is necking because they observe their engineering stress to go to show a maximum. To me, it's all for the reason that we don't think is the right reason for. So it is absolutely I'm sure it must be quite a bit of excitement that in exploring the consequence of the two model, you smell some very, very remarkable features that could only be interpreted this way. So they had some anticipation of shear banding upon looking at this. 79, of course, in that paper, so if anything, that paper did not discuss much is the step strain. Step shear, for example. Although the data existed since mid-70s. So data already existed, but that paper, if I recall very clearly, the fourth paper, it's all about nonlinear response. They talk about startup for both shear and extension. But step shear or step strain, if I recall, was not discussed there, although data exists. So why do I mention that? I mention that because subsequently you can examine this Dwyer-Edwards tube model and find there's one more additional non-monotheisticity in that model, or predicted, it's a feature of that model, which is what we described in chapter 12. That that I actually mentioned once before in chapter 12. There is so-called the damping function, which is this damping function. By its definition, is essentially the same quantity that we examined in chapter 14. That according to the tube model, this damping function, which remember is just a measure of the stress relaxation in terms of relaxation modulus, normalized by the equilibrium modulus. It, of course, because its strength softens, meaning relaxation is faster, it, of course, never exceeds 1. So it starts with 1 as a function of gamma, and it starts to have this red curve. Okay? Red curve is what the tube model, the Dou-Edwards tube model predicts. And I carefully draw it. It eventually, on the double log, has a slope of -2. And remember, this was, and some subset of data agrees with with this tube model. This caused me to realize that there must be something wrong after step shear. Things must break up because you cannot attain such a low stress. Why I say that? Because when you multiply the damping function with gamma, you recover the stress. And in the tube model, that stress is of orientational origin. Basically, it's all related to how chain stretch orients. So this is orientational function in the tube model, Q, which essentially is just proportional to stress, shear stress, xy. So we, I indicated before, I indicated now formally, that the tube model was also predicting that this stress at long times, how long? At times longer than Routh's retraction time. If you watch your stress relaxation at longer times, your stress will follow this red line. Which is odd because it says your stress, you see this maximum is also 2.2. It's the same, it's all the same feature. It's all from the same origin. So it says if you, Lord, if you, it says if you stretch beyond 2, I can, how do I know when the pen is engaged? If you stretch beyond 2 at longer times, the stress you observed is smaller than you stretched at 2. It makes absolutely no sense. Okay? No physics that I can comprehend. No. Okay. Maybe I'm too quick. But I had a hard time. Maybe I'm too quick. Maybe you can think differently, okay? Think about this way. You shear your sample, okay? You shear a sample to discrete, separate, same experiment but different amplitude. You shear it, and you reload, you shear it again at a different amplitude. And you perceive that upon stopping shear, the relaxation occurs uniformly, okay? If that's the case, it is, at least to me, it is really hard to imagine why I could result in a smaller stress when I use the higher magnitude to shear. When I look at my stress all at the same time, let's say 10 seconds, assuming you can shear it so fast that you can ignore how long it took for you to make the step strength, because that's in the theoretical limit is always infinitely fast. I just come from a world I don't believe that's possible. And the only thing I believe is possible if the sample breaks apart. Because if it does break apart, then it will just take advantage of that breaking. That's how you can relax your stress. Well, even there it's remarkable. You relax your stress excessively, right? Excessively, because you relax your stress lower than what it was there at a lower amplitude. Well, the more you stretch it, the failure is more dramatic so that it can take even more advantage of that. So you have even a more excessive amount of stress loss possible. Okay? I had a private conversation with people who are very familiar with the establishment of the tube model. I recall him saying that they are aware of this issue, that there is this, let's call this fourth maximum or whatever, fourth non-monotheisticity. They are aware of such a non-monotheisticity. I was telling him, hey, you guys don't know there's this one because you guys don't typically assign the meaning of this being the stress at long times. And they said they do. And they pondered around. Now I cannot recall, and certainly there was no clear answer, but basically it didn't cause them to be sufficiently alarmed. Let's put it this way. That's the reasonable word to say. Because otherwise you should be so alarmed by it, by seeing this feature of your own model, that you will think, you will really think differently. What is going on here? Do I capture this, or do I capture this for the wrong reason? Meaning, when I say capture this, I mean that there is a subset of data captured by my model, the tube model. So what does that mean you captured it? If it has the physics of this thing breaking, if they are in agreement, are we not saying that you should see a sample breaking apart? And if so, that's not quantum relaxation. And that was never raised, that question. Doesn't exist, that question. So, since I'm on this page, I just want to indicate formally that according to the tube model, numerically, the tube model basically predict, oh Lord, it's just the computer never. The tube model, or the Dou-Edwards model, basically prescribes the damping function, which is essentially numerically can be approximated by this function. And this function, of course, goes as 1 gamma squared. So even when you multiply that, it still goes with 1 over gamma. That's the slope on this side, right? That's the -1 slope here. Okay. If in fact this red line is nothing but gamma 1 over gamma squared divided by 5. This function has a maximum. Either about gamma equals 2. You can find out if you don't. So I don't know if by now I have confused you or not. But let me summarize. The tube model summarized in the language that we all know today, that this overshoot is yield point according to, we didn't know he proposed that, but according to Bryce Maxwell, in the same year, I think it was in Journal of Polymer Engineering and Science. I could be wrong, but it's cited in our book. And it's the same time fourth paper was published, also 1979, which speaks nothing but over-orientation as the origin of overshoot. So at least you know when we say yielding, there is a possibility that there is a structural failure, right? Well, something has to give in to stop linear, the elastic response. So, so I just want to, you draw your own conclusions. So I just want to indicate when you don't shear very fast, it turns out this indeed is just 2 tau, gravitation tau. It happens at. So the tube model has the magic of also producing overshoot without the concept of yielding and structure failure. So that's number one. Number two, so this is startup shear. Number two, I mentioned startup extension. Okay, startup extension, the tube model also has a feature that it will have a maximum. Two point something. It will have a maximum. And if it does, of course, the tube model cannot say you will have a necking. The tube model has to borrow a concept from considerate criteria, which is really, I don't know, maybe when we have time to kill, we'll talk about it. In my book, I talked about this considerate criteria used to speak about necking is really a reversal of causality. Because what we should find out is why the stress will drop. Well, we know what the tube model says why stress drops. It drops because area start to decrease. Okay, remember, this is just the total force. So this kind of maximum is the same as, you know what? Even the Maxwell model produces a maximum. A maximum is a linear model, so it cannot have any way to characterize a structural necking. So the considered criteria, I don't need to say more than the fact people have invoked this a lot in solid mechanics, that as soon as you have a maximum in tensile force, they will just borrow this argument that this is unstable against any perturbation of non-uniformity along the specimen. But there are lots of problems. I think I'm not. It's discussed in my book and in other places I give lectures on. But basically, I'm here to confuse you. The confusion I give you is experimental observations show that indeed the sample fails. This is a regime 2. If you still remember our discussion in chapter. If you don't remember, it's fine. We have the recording. Okay? It's in chapter 11. We talk about regime 2 failure. If it actually, I made a name for it. I call it tensile decohesion. And this is a regime where the failure is quite sharp, quite localized. And it occurs without a lot of window. It It occurs, oh Lord. Trying to be fancy here. It occurs, come on. Already selected that. It occurs, why? Can you believe it? I try to use the pink, because this is a big brush, right? I try to select a white color to cover this. Oh, Lord. It doesn't allow me to write it, to put things down. So basically it occurs without this part. It occurs fairly soon after maximum. Yeah, like I had here. It basically occurred fairly soon after maximum. So, if you like, if you are further happy with a theory and adding some other arbitrary argument about instability, which was presented in the original paper actually, then you can say the tube model even speak about failure of a specimen. Keep in mind, if you insist specimen could fail, why are we using filament stretching rheometry to indicate that you have steady state? So you see, the literature is full of controversy. The same people who says there could be necking is the same people who reported that there is steady state. Okay, what else? As I said, at this time, as early as this time, the consequence of tube model prediction for step strand was not fully evaluated and appreciated. And I already indicated that, not only I already indicated, I also in a previous lecture indicated that subsequently people find the tube model's description of step shear is the most successful. It's taken as the triumph because a subset of the data agrees with the damping function. It's just absolutely, in fact, it's summarized in the Dwight Edwards book as well. Okay, what else I have to say about tube model? It really, so for example, in fact, I don't think I'm doing justice. The reason I'm not doing it is we are running out of time, and also because I did carefully say this a couple of times. So for example, about the considered criteria of and necking, okay, and anticipation of necking based on considered criteria, I had a little section on it. Okay, so this so-called section 3, non-monotheisticity. Okay, sections chapter 16, section 1, subsection 3 has many parts. Okay, the first section is called, which of course is absence of linear response to step strand. Second is called shear, well, it's called stress overshoot upon simple shear. Third is called strand softening damping function, which we went through in detail. And we also went through that in chapter 14. And fourth is about excessive shear thinning, the symptoms of shear stress maximum. That's this. Symptom of shear stress maximum. And when I say excessive shear thinning, you should automatically know what I mean. The shear thinning is this feature. Okay? Excessive, it means the slope went beyond -1. In fact, in the tube model, it's -2. That's excessive. Because, why? Because by definition, when you multiply this with that, you still have -1. Right? You get it? It's all talking about steady state. If this is -2, then this, which is steady state stress, will be -1. Too much. Unphysical. So that's 4. 5 is what I just said. So please read 5 if you are. I in fact would urge my students in the class to read 5. It's a fun part. With that, you can see magically the tube model almost have all things covered. Amazing, just absolutely amazing. You can go home. I mean, basically it's done. It's all done. The specimen breakup is discussed as early as 79. Shear bending speculated as early as 79. Then we have the triumph step strand that fits a subset of data. We're done. And of course, that's what we thought was the case when we started. By now, I guess I should just recall very briefly for you why we end up doing something other than the tube model. Is because we were putting our samples. No, I think this is a fun part of history, right? In fact, it turns out this is not secret because I wrote this into that little summary paper. Basically, thanks to Professor Dilly, who urged us, who didn't urge us, who questions that wall slip can occur in this scenario with the sample being read. In drag shear, wall slip can take place. And we were naive enough to test it and not, I want to recall, not that we are very hopeful because I'm sure we know at that time. I swear I know at that time. The sample we prepared won't give you too much slip. We know that. I think we know that before any development of any further theoretical understanding. The understanding of chapter 6 on wall slip is largely there, except the steps here to show when data occurs. Remember, wall slip typically is discussing the steady state science, okay? Most of it. So, but that's fine because steady state is a very convenient limit where at least you can estimate what level of B you can produce, right? That's this. So we more or less know that we're not going to get a gigantic value of B over H. So we were just still trying to hope that we can at least, well, even if it jumped by a factor of 2, can we see that factor of 2? Well, the rest is history because we see, I carefully use this, we see that there is a big jump by applying certain stress. We see could be 2 order magnitude jump. for a sample that is this. So that's impossible. We later realized that this is what we called entanglement disentanglement transition. Right? And there, we further speculate that at least in this creep mode, maybe there will be no shear bending. So I want you to connect that the initial motivation was wall slip, but of course separately, in parallel, we are aware of the Duo-Edwards prediction of shear bending. And also we are aware of the unsuccess, the failure to observe shear bending at that point, up to that point. Right? And then I had a pretty dumb speculation that in creep mode, at least I can avoid shear bending. So they have several scenarios leading us to think that we should do particle tracking velocimetry to observe shear bending. And lo and behold, we did observe shear bending, and that changed our world forever. Because that's when we start to realize, gee, we didn't know Maxwell. We didn't know Bryce Maxwell whatsoever until many, many years later. But we realized, independent of him, that this must be a yield point. We are not an expert on tube model, but we are pretty certain that this concept of yielding is not readily available from the tube model. So I think I will pick up from this point next time. I know how much time. I think we had an hour about. So let me just have at least a little beginning of that. So we will come back and talk about how to think about shear bending, yielding, and most importantly, in fact, this part is quite amusing. I know this data is unphysical. It gives us breakup in the sample. But so we went ahead and observed non-quiescent relaxation. Okay, but the physics behind that non-quiescent relaxation was still very elusive. So it's kind of actually funny. We know something is wrong, but we don't know why it does that. But nevertheless, we went ahead to see that first. So in any case, we'll come back next time to talk in detail about our picture. So in this picture, which is really completed in the description of Journal of Chemical Physics 2007. But just to give you the timeline, but actually it was all clear by the summer of 2006. And just to give you the timeline, it's the winter, spring, 2005-06. That's when we had this non-quiescent relaxation phenomena established or discovered. Almost as a prediction, actually, because we know there was some trouble with this non-monotheisticity. So, of course, just from the point of view of timeline, the Oh, Lord. It went to a play mode on that screen. So just for the timeline, there is the APS March meeting, 2006, where I just got hold of. It's beyond you guys' time. 2006, your baby is still, right? 14 years ago. Over 14 years ago, right? Over 14 years ago. I got hold of a little thing called, Apple product called iPod, whose screen is about this big. 3 inch by 2 inch by 2 inch, or 3 inch by 2 inch by 2 inch, something like that. We were able to load our video onto this little iPod and went to the APS meeting to present a poster where we showed this little iPod. People gather around and say, yeah, what? And somebody who is familiar with step strand, he did step strand work a lot himself, saw the non-quiescent stress relaxation. He uttered a word involuntarily. He couldn't help. Some people hear it, but he wouldn't do that again publicly, I guess. I'm just making a joke. He uttered a word, my God, we are all screwed. So this picture, so this is still very perplexing. Let me tell you why it's perplexing. By that time, if you do a startup, we already have the knowledge shear bending would occur here, okay? However, this step strand experiment, as you know, is we stop it here. So the sample is far away from breaking apart, yet upon stopping, you will induce the breakup. That's the phenomenology. Non-quiescent relaxation. Of course, you need to reach certain magnitude. Today, I think in the book, we call it elastic breakdown. But essentially, basically, a factor of 2 is enough. But why this happens? I mean, how can termination of deformation cause it to occur? If there is ongoing deformation, it will not occur for this much time. So that was the puzzle. It's really, and speaking of sleepless night, that's really the time we were really puzzled by. So luckily, I had a chance to go to visit abroad, many places during the summer, and gave it about same talk 10 times. And thinking about, with no explanation, I just said, we reported this. What is this? By the time of it, we figured out what had happened. And this all has to do with when I come back next time to tell you about the 3 forces in the paper. It's a absolutely exciting time because it's up to that point we really have no clue. And the 3 forces, only one is what you are familiar with. So when we come back, I will tell you the one we are familiar with. We speak a lot already. The retractive force. Why? Because it supposedly is what we learned from Robbie elasticity idea. So this one we are familiar with. The next 2, to us, it was unknown. And we certainly have not found out who know that other 2 forces from the literature until we propose it in 2007. So we'll do that next time. I will give you a more careful formulation of what this force is with the right symbols, and introduce other two forces as well. Okay, so with that.